All right, so let's begin. I hope my screen is visible. So, welcome to another week of Introduction to Astrophysical Fluids. This is week 8. My name is Rohan and I am a TA for this course. I'm a PhD scholar at IISc Bangalore. And so this week we will start with a brief recap about the previous week, and then we will move on to study about stellar oscillations, and then we will study about fluids in a rotating frame. Okay, so right. So last week we studied different kinds of instabilities. So, for example, Rayleigh-Benard convection, Jeans instability, Rayleigh-Taylor instability, and Kelvin-Helmholtz instability. And prior to that, we also studied another instability, which was the Schwarzschild instability. So, all of these different instabilities occur due to uh, different, you know, conditions. For example, Schwarzschild instability, as I said, occurs due to the fact that when you have some fluid which has a different density, well, you have a bubble inside a fluid, and that bubble has a different density than the surrounding. And if it has a lower density, it will rise up. And then after rising up, if it still has a lower density than the surrounding, it will keep on rising up, and that will give rise to that to an unstable condition. Right? And so yeah, so that occurs due to uh, you know different density of a bubble in um, than the surrounding, right? So yeah, so right, and then there is Rayleigh-Benard convection, which occurs when you have you know so basically when you have a heat bath, right? So for example, in this video, if you see, so you have this heat bath, and the fluid is heated from the bottom, whereas at the top it's much colder, right? So the fluid actually circulates from the bottom to the top, and where it encounters the colder fluid, it replaces the colder fluid at the top when the colder fluid moves down to the bottom and then again gets heated up, and the circulation continues. And that's how this Rayleigh instability occurs. And you see this hexagonal cells which are typical of these kinds of Rayleigh-Benard convection. So after that, we studied Rayleigh number, and this is the plot of Rayleigh number with respect to wave number or wavelength. So if you can see that at a fixed Rayleigh number, you would have these wave numbers which will be stable, whereas these wave numbers which will be unstable, and then again some other higher wave numbers which are stable again. So there is a fixed um, region or fixed values of wave numbers which are uh, unstable for a particular Rayleigh number. Okay, and right. So yeah, we studied the condition for Rayleigh stability and Rayleigh instability in the previous lecture. So after that, we went on to study about Jeans instability, where we say that this instability occurs due to uh, you know, due to basically gravity, right? And so when you have a dense matter somewhere and it falls under gravitational collapse, the matter, falls under gravitational collapse, and we have to calculate like what is the length scale of that matter which would cause this collapse, and what should be the mass of the matter such that the gravitational collapse happens, right? So that length scale is given by this Jeans wavelength lambda j, which is given by this uh, this expression. And if the mass, exceeds the gene's mass, then that uh, part of the matter will collapse under gravity. And that's how actually stars are formed, which we see stars forming from nebula. So nebulas are these uh, gas clouds of cold, which contains very cold gas, and they will have pockets of, so these gas clouds are not uniform, so they will have different pockets of high density and low density regions, right? And if in a region which has a length like this, of this order, and whose mass is of this order, then that will actually collapse into uh, something which can form a star at the end. Okay. Okay. So another instability that we studied was the Rayleigh-Taylor instability, which occurs between two fluids which have different densities, two immiscible fluids with different densities. So, for example, well, we all know that denser fluid will try to go at the bottom, whereas lighter fluid will try to stay at the top. But what if you have uh, lighter fluid at the top? Uh, Sorry, a denser fluid at the top and lighter fluid at the bottom. So what will happen is that if you perturb the system a bit, then it will form these type of structures which are typical of this Rayleigh instability, Rayleigh-Taylor instability. So this is the dispersion relation for the Rayleigh-Taylor instability. For example, the sigma is basically, so if you remember, like we represented all these physical quantities like velocity or density uh, as some wave functions, which are rho, something like f hat e to the power of I sigma t plus kx or something like that. So the I sigma t, so that is the sigma, right? So now we argued that if this sigma is uh, you know uh, real or imaginary, and if it's imaginary, then this instability will basically mm, you know decay, or if it's positive, or uh, you know uh, if it's real, then the instability will grow, right? So for example, so this term, the second term, is the term that is coming from the surface tension. This gamma is the surface tension coefficient, so which is the stabilizing force, whereas this difference in the density is giving rise to this buoyancy force, right, which is the destabilizing force. So the buoyancy is trying to get the lighter fluid at the top and the heavier fluid at the bottom, which is prevented by this surface tension term. So if this term is greater than this one, then we can say that well, um, the the surface tension wins, and therefore this system will be stable. Whereas if this term is greater than this term, then sigma will be real, and in that case, so if it will be I sigma t, right? So if sigma is real, then we will have some oscillations, right? It will not exponentially grow or decay. So there will be oscillations, and then these are stable uh, instabilities. I mean, yeah, the system is stable, right? The Rayleigh instability do not occur. Similarly, the Kelvin-Helmholtz instability occurs when we have two layers of fluid, which could have same density or different densities, but the main distinguishing factor for this instability from the relative instability is that those two layers of fluid should have different velocities. Right? So if you can imagine two layers of fluid moving past each other, one with higher velocity, another with lower velocity, then there is just some shear between the two layers of fluid, and that shear is causing these structures, right? So if you zoom in on the structures, you'll see even finer structures over this, right? So these are some vortical structures that you see, which are typical of this Kelvin-Helmholtz instability. And in the similar way, we can represent this thing as something like, this is the dispersion relation, the same sigma factor, so the coefficient of the time, right? So this is the S. And again, we discussed all the cases, like what if rho 1 equals to rho 2, what if rho 1 is different than rho 2, and what if u2 is greater than u1, u2 is less than u1, and all those things. And depending on those things, we can estimate whether S is purely imaginary or if it's purely, you know, sorry, it cannot be purely real, but if if it has a real part, right? So if it has a real part, then this will decay. Whereas if it's purely imaginary, then you will see it will be stable, right? Right. So, yeah. So that was the discussion that we had till last week. And as I said, this week uh, we'll be studying about stellar oscillations, and uh, then we will move on to study about the fluid dynamics in a rotating frame of fluid. Okay. Okay. So, right. So before we go into doing the linear instability analysis of these stellar oscillation equations, I just want to give you a brief idea about what we are gonna do. So let me go back to my notebook and then just explain what stellar oscillations are all about. So. Let's see. Okay, so let's say we have some star like a sun, and we introduce some small perturbations to the surface of the star, right? So if we have some perturbations like this, and and then we would try to understand that whether these perturbations grow with time, or they decay, or how do they evolve, and what are the frequencies that we observe with respect to these oscillations, right? So these are mostly surface oscillations, and therefore our system that we are going to study is that we are going to perturb the boundary or the surface of the star, just like has been shown over here in a small way. So let's say our initial radius of the star was let's say r naught. Okay, so this is r naught, and after perturbation, the radius of the star becomes r naught times 1 plus delta. Right? Delta is the small perturbation. Right? So volume of the system will be, cube, r naught cube plus 1 plus delta cube. Right? And well, the mass of the star will be same before and after the perturbation. So the density, which is mass by volume, since mass is same, it will be inversely proportional to volume. So it will be rho naught times 1 plus delta whole to the minus 3, where rho naught is the initial uh, density m by v naught, and v naught is r naught cube. Well, it is 4 by 3 pi r naught cube, but we are just seeing the variation. Anyway, well, you can add 4 by 3 pi over here as well, and here as well. Okay, so right now, what about the uh, pressure? So the pressure is P naught times 1 plus delta with minus 3 gamma, right? And which is equals to P naught into 1 minus 3 gamma delta. So this is just doing binomial expansion up to first order. If we can also have higher order terms in delta, but we are just since delta is very small, we are just keeping it to the lowest order, right? Okay. And similarly, rho is also 1 minus 3 delta, right? Okay. So, okay. So this is the setup that we have. Now we want to solve the uh, Euler equation for the star, right? Okay. Now, in the before the perturbation, what could be the Euler equation? So before the perturbation, well, all the quantities were has a subscript of naught, and it was in steady state, so the del del t would be 0, and therefore the equation would be dp naught dr naught equals to gm by r naught square, right? Now we just want to calculate this quantity, this equation, after the perturbation. So this will become t equals to minus 1 by rho is rho naught times 1 minus 3 delta. So we're just replacing everything, uh, all these terms from here, rho and p and everything. So dp is 1 minus 3 gamma delta divided by dr naught times 1 plus delta minus gm by r naught square into 1 plus 2 delta. So p is replaced by this, and r naught r is replaced by this thing, and gm by r square. So r square will be r naught square times 1 plus delta whole square, and again 1 plus delta whole square is 1 plus 2 delta plus delta square, but we are neglecting terms of second order in delta or higher. So by just simplifying this, dp naught dr naught 1 minus 3 gamma delta 1 minus 2 delta minus gm by r naught square 1 minus 2 delta, right? So I'm just taking this in the numerator, and therefore this will be 1 plus 2 delta whole to the power minus 1, and then again doing binomial expansion, it's 1 minus 2 delta, right? And yeah, so this will be dp naught dr naught times 1 plus 2 delta minus 3 gamma delta, right? So yeah, so again, like doing the same thing for this. So 1 minus 3 gamma delta times 1 plus 2 delta, and keeping only terms of the order of delta, neglecting all higher order terms, we'll get this, and this will be same. Now we are going to use this relation over here, right? So gm by r naught square is 1 by rho naught dp naught dr naught, and from there we can like add up these two. So this delta will be gone, and we will be left with 1 by rho naught dp naught dr naught 3 delta gamma minus 4 by 3. So now we want to see, like, so we have been doing studying these instabilities for a long time, and we have understood that, you know, so this this perturbations that we have introduced to the star, they should decay with time, and if they do not decay, we get ourselves an instability. So basically, the velocity, so the dv dt should, decay with time. So the velocity should decrease with time. So therefore, dv dt should be negative, right? So dv dt should be negative for it to be stable, for stability. And dv dt negative, so you see that there is a minus here. Rho naught is positive, p naught r naught. So this term is positive, and therefore gamma should be greater than 4 by 3 for stability, right? And for instability, gamma should be less than 4 by 3. Right? So I think so. In the lecture also that they have given some explanation that why this causes the instability is because, so you see that there is a gravity and then there is pressure, right? So now if you introduce this instability, it's up to the pressure to, overcome the gravity. So for example, if you remember the polytropic equation of state. So this is pk rho to the power of gamma, right? So you see that if gamma is high, so that means pressure will be high, right? So pressure will respond much quickly to changes in gravity, right? And therefore, any perturbation that you create, pressure will respond immediately, and it will, try to reduce the perturbation, right? It will balance gravity very effectively. Whereas if this gamma is small, the pressure will not be able to act very effectively to counterbalance the gravity, and therefore the gravity will dominate and it will cause this instabilities. Right. So that is the explanation. Now, what kind of gases have this gamma equals to 4 by 3? So if you remember from our high school studies, that gamma is basically the adiabatic factor, which is Cp plus Cv. And if you see for a photon gas or for radiation, gamma is exactly equals to 4 by 3. So for any relativistic gas or gases which are moving at very high speeds, gamma is equals to 4 by 3. So photons, photon gas or radiation, right? Or relativistic. It's also called the relativistic equation of state for relativistic particles. Gamma is equals to 4 by 3, right? So, right. So, for example, like gamma is the degree of freedom, right? So, for normal monoatomic gases and all, gamma is 5 by 3, if you remember. Whereas for relativistic gases, gamma is 4 by 3. Generally, it's somewhere in between 4 by 3 and 5 by 3. But here we see that for stability we need gamma is greater than 4 by 3. So therefore, in most of the cases, uh, this star will be stable. Okay. Right. So okay. Now here is one analysis that is not given in the lectures, but I thought this is an interesting thing to uh, you know to mention over here, because this is an active area of research and many people study these things to study the stellar oscillations, and you'll find many papers on this, right? And the way they do these things is by this analysis. So I'll not go into detail of this analysis because this will be very lengthy, and like they have a lot of calculations. So I'll not do the calculations, but I will just explain what the steps are and how you go from, uh, go from the simple fluid equations to understand what are the different modes of oscillations that are available for these systems. So this is the simple equation of continuity and the Euler equation that we are going to solve. And along with that, we also know the the Newton's gravity equation, right? So which is del square phi equals to 4 pi g rho, right? So these three will be our basic equations. And what we'll do is that using these three equations, we'll introduce perturbations of this density and velocity, and pressure, and also the potential, the phi, right? And those perturbations are represented as dash. So rho dash is basically the uh, perturbation, and we'll neglect all higher order terms in the perturbation. So rho prime square and all those things we'll neglect. So if you perturb this equation, it will come down to this thing. So xi is nothing but the velocity actually, right? So the unperturbed velocity was 0, and the perturbed velocity is xi. Okay. So actually, I have So let me just show this. So actually, I will share one material with you, which will have these things in somewhat more detail. So I'll share them in the drive. So this is the paper that I'm following, and so this material I will share. So this is the equations, and this is a 28-page material, and separately I have made another. Uh, um, yes, another document which also I will share, and this contains the explicit derivation. So these derivations are pretty lengthy, so this I will share with through them in the lecture right now. Okay, so right. So as I said, like after introducing perturbations, so this will look, the equations will look something like this. So this is the continuity equation, and this will be the uh, this thing, the Euler equation. This is the gravity equation, right? And this is the equation of state, right? So we have actually done this before. We have derived how to get the perturbed equation from the original equations in one of the previous analysis, right? So this will be straightforward. I think we have done it before in class. So if you are wondering how to get here from here, you can just look at one of the earlier lectures. But the main difficulty is from going from here to actually here, right? And uh, in the in this paper which I showed you, this derivation is not actually given. So therefore, I made a separate document which I showed you also, where I have derived how to get from here to here in detail in some steps. But the main idea is that so these are the perturbed equation. So you understand the physics, right? That this is the density perturbation, this is the velocity perturbation xi, and well, p prime is the pressure perturbation, and so on. So it turns out that all these perturbed quantities, p prime, rho prime, phi prime, right, will can follow a solution of this. So this is like an ansatz that we are gonna use, right? And psi we are gonna take something like this, right? And then we'll put these values into these equations, and then we will see what are the solutions that we get. So for example, let's say you see this xi r, right? So xi r is basically um, the radial part of this xi, and this ylm are the legendary polynomials, right? So you might have been familiar with these in electrodynamics, right? So these are spherical harmonics. So yeah, so I will not go much into detail, but these are, let's say, some polynomials which are dependent on this L and M, right? So this is the radial part, and this is the vertical part, horizontal part, e to the power of minus I over t. So these are just we are proposing that these functions will have a solution of these forms, right? And so this is just our assumption, right? And using this assumption, then we put these assumptions back into these equations, and then we solve these equations, and finally we obtain these relations, right? And now this is what has been done in the document that I just showed you, is that how we derive these equations. So these are our base equations, right? As we saw, then we put these values into these equations, right? And this is step one, where I put these values into the continuity equation, and from there you obtain this relation. And finally, if you put into adiabatic the equation of state, you obtain this relation. If you put it into the momentum equation, you get two separate components of the momentum equation. One is the radial component, one is the horizontal component, right? And from there you get two different equations, this one and this one. And similarly, if you put in the Poisson equation or the Newton's law, so you get this relation. And finally we eliminate this epsilon h and rho prime, right? Using this, and we do some calculations, and finally we obtain this equation. So this equation is basically similar to what we have been so this equation is yeah, right, the last equation that we are seeing over here, right? So yeah, you can go through the derivation. It's a bit lengthy, but the main point, or the physical motivation behind these equations, is that you see the so for example, let's take out this equation, right, the second middle one. So here we have something like the n naught square, which is the Brun-Weisser frequency that we studied in the previous lecture, right? So, and this SL is something called the Lamb frequency. Okay. So we see that these oscillations are dependent on these two frequencies, SL and N naught. So, and for different values of L and M, so these are what are the modes that we will get, right? So, so from here, from by solving these equations, you can get the value of psi r, right? And all these primes, p prime, rho prime, phi prime, okay? And then you put the solution over there. So the final solution will look something like f prime yml, right? And yml, as I said, are legendary polynomials. So the final solution of these equations would be, something like this. Okay, and this legendary polynomials. So, for example, if you remember in electrodynamics or in even quantum mechanics, while solving the hydrogen hydrogen atom solutions, right? So we have this radial equation and this azimuthal equation, and solution of this azimuthal equation of this legendary polynomials. And you see that these legendary polynomials take different shapes, like similar to dumbbells, like sine square theta and cos square theta minus one, and so on. So they will have these kinds of structures. So for m equals to 0, l equals to 0, it will be mostly spherical, right? Whereas if you go to higher l's, it will deviate from sphericity. So this will have a lower value, the other hemisphere will have a higher value, and this will how the oscillations will look like. So this is basically the physical motivation, but the mathematics is a little bit complicated. Okay, right. So that is it for stellar oscillations. Okay, let's move on to the next part then, which is the centrifugal Rayleigh criterion for centrifugal instability. right? So okay, so now let's say we have a star and it is rotating, right? So the star is rotating, and now we wanted to understand that should the star rotate as a solid body, or should the star have a differential rotation? So what do I mean by a solid body is because is that so when you have a solid um, object and you rotate it, so let's say you rotate a football, and you will see that well, the football is hollow, but let's say you rotate some solid object, right, which is not hollow from inside. So you will see that all the points in that object will rotate at the same angular velocity, right? The angular velocity will be same. Okay. So that is what a solid body rotation means. So will the star rotate with all layers or all shells at different radius with the same omega, that is the same angular velocity, or will different layers or different shells of the within the star will rotate with different angular velocity? Will it have different omega? So, okay, naively, we can understand that, if there are a lot of viscous forces, so we studied viscosity, right? So, viscous forces are something which are, causing the shear within two layers, right? And you can also, visualize viscous forces. Like, for example, you can have, you have honey, right? So, honey is more viscous than water, right? So, if you have a jar with the water, and if you have jar with the honey, and if you rotate the jar, it's more likely that the honey will rotate together, right? It will have a solid body rotation, right? Whereas the water, in the case of the water, the since the viscosity is less, different layers of the water, different shells at different radius of the water will might have different omega, different angular velocity. So viscosity is actually helping in, it is basically adding shear to the next layer, and it's telling the next layer that you have to rotate with the velocity of the previous layer, and therefore all the layers will have, similar velocity, similar angular velocity, right? So viscosity is something which is causing this solid body rotation. So now we wanted to understand that what causes this differential rotation, and whether differential rotation can be sustained in stars, or stars should have solid body rotation. Well, it turns out that stars generally have differential rotation. In fact, sun, our star, it also has a differential rotation. It does not have a uh, you know uh, solid body rotation. So either the viscosity is not too high, or there is something else going on. So that's what we want to study over here. So for example, let's say we have some concentric cylinders, right? So here we have, and these two different shells are rotating at different velocities, omega 1 and omega 2, right? And so for example, let's say you have some well let's say, yeah, so for example, the example that I was giving, that you have a jar of water and you rotate the jar. So you rotate the jar at some particular angular velocity, right? So the layer of water that is closest to the the boundary of the jar will rotate with the same velocity, or it will rotate it with the closest to that velocity of the boundary of the jar, right? Whereas as you go inner and inner, the velocity and the angular velocity of the layer of the water will decrease, right? So that is what has been shown here, and that will cause a differential rotation of the water, right? So right, so here is a schematic diagram of let's say you have two shells, one with omega 1, one with omega 2, at different radius r1 and r2, and we study the so what we do is we do an experiment that, if you have some fluid which is over here, like you take some element of the fluid which is at omega 2, and you just exchange it, uh, you just bring it to this position at r1. So from r2 to you bring that fluid to r1. So something which we have been doing in many cases. So for example, if you remember in Schwarzschild instability, while we are trying to derive the relation between uh, relation for Schwarzschild instability, we actually took the fluid, a bubble inside the fluid, from one height to another height, right? And then we studied whether that blob of fluid will keep on moving up or it will go down. And if it goes down, then we say that okay, it's stable. And if it keep on goes up, we say that okay, that system is unstable. So we are going to do a similar kind of thing. So we bring the blob of fluid from R2 to R1, and if it goes back, we say it's stable. Or if it stays here or goes further in, then we say it's unstable. So that's what we do over here, and we check what is the initial energy of the blob of fluid when it was at R2, and this energy was given by this thing, H1 square by R1 square plus H2 square by R2 square, right? So and similarly, if we have the blob of fluid at new location, so uh, this is given as, well, so h square is basically omega square r to the power 4, right? So okay, I forgot to mention over here, but anyway, so h square is uh, r to the power 4 omega square. So if you see over here, and therefore h is basically omega r square, okay, or r square omega. So it is angular momentum per unit mass. Right? So this energy is given as I omega square, right? So energy of a rotating body is given as half I omega square, and this is exactly that thing. So rho is mass, I is basically of the order of mr square, right? So rho dv is mass, and if you solve this, it will come out to be r square omega square, right? So yeah, so this is I omega square, and this is the energy of the fluid at the initial point, and this is the new energy of the fluid if when you bring this blob of fluid from R2 to R1. So this will be okay. So you not only bring this blob of fluid from R2 to R1, you actually replace this fluid. So since you bring this blob to R1, so you have to get one different blob which was initially at R1 to R2. Right? So you just interchange two blobs of fluid at two different radii, and this is the new energy, right? So this is the energy of the replaced blob from R2 to R1, and this is the for the replaced blob from yes yes R1 to R2. That's right. So right. Now we argue that if the new energy is less than the old energy, then we say that then the new configuration is more stable. So that means that the fluid will try to go from here to here, and we will have this instability, right? So because the system will always try to go to a lower energy state. So if the new configuration is lower energy, so that means that the system will try to interchange always, right? It will not try to it will not want to have these differential rotation because it is trying to interchange over here. On the other hand, if this configuration was stable, the initial configuration was stable, then we would say that okay, the system wants to have differential rotation, and they want to go back to being, rotating at different omegas. So so that will be a condition for stability. So if we just check the difference in delta E, so this is how the difference is. And as I was saying that if this thing is negative or positive, and depending on that it will be stable or unstable. And the condition turns out to be that this h square, so ddr of h squared, so that means uh, h2 square minus h1 square is should be less than 0 for instability. So this just means that as r increases, h square should decrease, right? So h square should decrease with increase in r. So that means that, h square is just the angular momentum, as I said. So as you go further, the r increases means you are going further from the center. So as you go further, the angular momentum should decrease for instability, right? Whereas if you want the system to be stable, as you go further, angular momentum has to increase. Right? So that is what this condition is talking about. Right? Okay. So this is the plot for omega 1, omega 2. And if you have, so this is the solid body rotation line. As I said, solid body rotation means all the points in the body is rotating with same omega. Omega 1 equals to omega 2. So this is the region for quasi-Keplerian flow. So I'll just explain why is it quasi-Keplerian. But you can see from here that, so this is the region between omega 1 equals to omega 2 and omega 1 r square equals to omega 2 r square, which is this thing, right? And above this is the condition for instability. So this is the Rayleigh unstable flow. And in the quasi-Keplerian flow, you have this omega 1 greater than omega 2, right? But you have this angular momentum. So if you look from this diagram, so the omega 1, the inner layer will have a higher angular velocity than the outer layer, but the angular momentum of the outer layer would be higher. So inner layer has higher angular velocity, and outer layer has higher angular momentum. So as you go outward, the angular momentum will increase, but the angular velocity will decrease. Now, why is it called quasi-Keplerian? Because this is similar to what we observe in the Keplerian flow. So if you remember, so when we did, let me see. So when we did the thing for in one of our previous weeks, let me open that up. So yeah, so this is the condition for Keplerian motion, right? So omega is r to the power of minus 3 by 2. So omega decreases as we go to higher r, right? Whereas angular momentum, if you see, it increases with r, right? So it increases with r to the power of, well, root over of r, and omega decreases as r to the power minus 3 by 2, and that is exactly what is happening over in this region, right? So this region is also stable, and also this region is also stable. So everything below the orange line is stable, and above the orange line is unstable. Okay, so that is what we have from this criterion. Right. Okay. Okay, so now we will study fluid dynamics in a rotating frame. So before that, so these materials for the fluid dynamics in a rotating frame, you can study from this book, the Kundu Cohen book, right? And well, this is not actually chapter 14, so this should be 3 or 4. Actually, I have the book open. Let me just check. So I think it would be So chapter 5 is there, you can study. But chapter 5 is mostly for the, yeah, chapter 5 is also contains the Coriolis force and everything, those things. But okay, so this is the rotating frame, yeah, description. So this is chapter 4, right? Yeah. Yes. So chapter 4 and 5 you can study. Okay. So this will have a good background of the rotating frame, and apart from that, you can also uh, study the book on Arnab Rai Chaudhary. So this also has these things. Okay. So okay. So this is the actually the equation of any quantity uh, if you study it from a rotating frame. So I will just quickly motivate how we get this. But what is the first equation saying is that, so you have, let's say you have any vector quantity p. It could be, position or velocity or, uh, well, let's say any other vector, right? So yeah, so it could be any vector in the um, and this subscript f is represented by the fixed frame, right? So let's say you are a fixed observer and you are in an inertial frame, or let's say you are in the lab frame, and there is some rotating body. So in the lab, you are, let's say, rotating. You have a jar with water in it, and the jar is rotating, right? Now, this F is your frame, the fixed frame, and then there could be another, reference frame which is added to the rotating jar, right? The jar is rotating, and there could be another frame which is attached to the jar. So this subscript R is basically representing that frame, that set of coordinates that are fixed to the rotating object. So this equation tells about how the vector actually transforms from the fluid frame to the rotating frame. Actually, the time derivative of the vector, right, transforms from the fluid frame to the rotating frame. So the fluid frame, sorry, not the fluid frame, the fixed frame. Okay, by fixed I mean the stationary frame or the lab frame. So this is what you observe actually, the from the fixed frame, whereas this is the what the jar observes, right? So so the fluid will also have some motion with respect to the jar, right? So as we are saying that the fluid is not exactly moving with the jar; it could have a different velocity, or uh, if p is the velocity vector, or it could have different vectors with respect to the frame that is fixed to the jar or the rotating frame. Now, well, just to simply show a derivation of this quantity, like how this equation comes about. So this is actually given in Goldstein book, but like there could be any book which you can refer for this. But okay, so let me just show you. So this really comes from the fact that uh, while the frame is rotating, the unit vectors that are attached to the uh, rotating frame are also changing in time, right? Because the rotating frame is you know attached to the jar, and since the jar is rotating, the frame is also rotating along with it. So the unit vectors will point in different directions at different points of time. So for example, let's say that you have this quantity p, which can be represented as px prime I prime. So these prime quantities are basically the in the rotating frame, right? J prime, whereas non-primed are the in the lab frame. So if you have dp dt in the rotating frame, they will look something like this, right? They will look something like this. All are primes, right? Now, when you try to go into the fixed frame or the lab frame, you also have to, take care of the fact that these uh, I prime, J prime, and K prime are also changing with time. So up to this far, it's the same, and then you will have some additional terms like px prime, di prime dt plus py prime, dj prime dt plus pc prime, dk prime dt. And what are these quantities? Di prime dt is basically omega cross I prime. Similarly, dj prime dt is omega cross j prime. Dk prime dt omega cross k prime. So yes. So now this part. So this part will reduce down to omega cross px prime I prime plus py prime j prime plus pz prime k prime, which is basically omega cross p, right? So therefore, if you see the final expression will be dp dt f equals to dp dt rotating. So this is the dp dt in the rotating frame, which is given as this, plus omega plus p. So this is a quick motivation, right, of how we get this equation. Okay, so now so this is the derivation is okay, but the impact of this equation is very huge, as we'll see shortly. So let's say we replace the p. As I said, p could be any vector. So let's say we consider that p is the velocity of the fluid, u. We replace p with u, right? U that is as observed from the fixed frame by the observer. So, so because this is the quantity that we are going to measure, right? From our perspective, we are not going to sit on the rotating jar. So we are at a fixed frame. So we'll measure only this u f. So if we put uf in place of p, so this is how the equation will become, right? And if we just break it down, so for example uf over here, right? So right, so uf is basically ur plus omega cross r, right? So this is just the uh, relative velocity. So for example, okay, let me just also show this how it becomes. So before putting u in place of p, we can also so instead of putting directly u, we can also put x in place of this p, right? So for example, if we just, you know, so dp dt in the fixed frame is dp dt in the rotating plane plus omega cross p, right? So in place of p, we can put the position vector of the particle r, right? So if we just put that, this will become dr dt in the fixed frame equals to dr dt in the rotating frame plus omega cross r, right? So dr dt is the velocity, which is uf in the fixed frame, equals to ur, the velocity in the rotating frame, plus omega cross r. Okay. So this is what if we put p equals to r, right? So we got uf equals to ur plus omega cross r. Now what we'll do is we are going to put p equals to u, okay, and this is what we are getting. So if we put u p equals to u, we are getting this thing, and as we also saw, uf equals to ur plus omega cross r. If we put p equals to r, so we just replace uf with this thing. Similarly, we do that over here as well, right? And that's how we break it out, and then we uh, you know take each of the terms. So ddt of ur plus omega cross ddt of omega cross r, right? And ddt of omega cross r is basically, so omega is the fixed, is a constant. It's not varying. So this will be omega cross dr dt, right? And then if we break up this thing, so this will be omega cross ur plus omega cross r. Okay. So this is what it will become, right? And if you see, so this dr dt is again ur. So this will be omega cross ur plus omega cross ur. So this will be 2 times omega cross ur. Right? So this is the term 2 times omega cross ur is what is called the Coriolis force. Right? And so we have studied this Coriolis force in our high school as well. And this is what is causing things to, so for example, in Earth, depending on which hemisphere you are in, the water, while flowing down a faucet, it will either flow in the clockwise or the anti-clockwise direction. That is the Coriolis force that is causing it, right? Because the Earth itself is rotating, and so basically, this rotation is giving rise to this force, Coriolis force, omega 2 omega cross ur. Okay? And this omega cross r is, if you remember, so this is basically the centrifugal term, right? That arises to the centrifugal force. Okay, so now we have a relation between the fluid velocity in the fixed frame to the fluid velocity in the rotating frame. And similarly, we can accordingly, modify our equations and modify the Euler equation like this. Okay. So if you remember, du dt equals to minus del p by rho nu del square u. So up to this it was okay plus gn. Up to this term, it was what we studied earlier. But this omega square r, this is the extra term that we are getting because of this thing, omega cross r, because of this term. And this twice omega cross u is, as I said, is because of this Coriolis force. Okay. So these are the two extra terms that we got in our Euler equation, right? Now we are going to simplify this, um, this omega cross r, this expression. And what will come out of this is this thing. So yeah, let me just also show how this comes, because this was also not shown clearly in the lectures. Okay, so what we have to show is omega cross r equals to half del omega cross, okay, let's see, half del omega cross r whole square, right? Yeah. Is there a question? Okay. So okay. So omega cross r, the cross product is basically omega times, well, mod omega mod r sine theta, right? So that is basic vector law. And if you square this, so this will be omega square sine square theta, right? And sine square theta is basically 1 minus cos square theta, right? And so this will be omega square r square minus omega square r square cos square theta. So without the vector sign means I am just taking their magnitude, the mod of them. Right? So omega square r square minus omega square r square cos square theta, and cos square theta is just, so omega r cos theta is the dot product, right? So omega square r square minus omega dot r whole square, because omega dot r is omega r cos theta whole square is this thing. Right? So this is one thing. Another thing is that we also know this identity, A cross B cross C is equals to A dot C B minus A dot B C. So we are going to use this identity on this term to reduce this term, omega cross R. So if we use this, we are going to get omega dot R omega minus omega dot omega. So A dot B is omega dot omega, which is omega square R vector. Okay. Now let's look at this thing again. So this is half del omega cross r whole square. So this will be half del omega square r square minus omega dot r whole square. This will be in turn equal to, so as I said, omega is constant, right? So this will be del r square, and del r square is 2r, right? So that 2 will cancel with this 2. So this will just be omega square r, right? Well, let me actually write another step. So this will be half omega square del r square minus half omega half delta omega dot r whole square, right? And so this will del r square will be 2r, 2 will cancel, so this will be omega square r minus, so this delta of this thing will be twice this thing, right? So just chain rule. So this 2 will cancel again with 2. So this will be omega dot r, right? And then there will be another derivative which will leave out omega, right? Because del r is 1. So this is the thing that we get over here. And this is exactly equal to this thing, right? With a minus sign, of course. So minus of, well, I hope I had a minus over here, right? Yeah, there is a minus over here, right? So the identity should be minus of this. Okay. So minus of this is equal to this thing, right? All right. So okay. So now we saw that. Now we can replace this omega cross r with this term, and the thing that we get is this thing, this equation, which is just coming from the Euler equation. So this is a modified Euler equation, and this is the, so if you see that this term, right? So the original Euler equation was this thing equals to del p by rho plus gradient of phi plus the viscous term plus the Coriolis term. Now, instead of phi, we have some different factor, which we now call the phi effective, which is the original phi due to the gravitational force modified with the centrifugal force. Right? So this is the phi effective, which is gravity plus the centrifugal. Okay. Now, okay. Now we introduce another important parameter, which we call the Rossby number. So, which is coming from the fact that if we, neglect if you consider steady state, so del t will be 0. If you consider neglect the viscosity, that is for ideal fluid, this term will also go to 0. And we neglect the uh, pressure force and the gravitational force. So then we are only left with this term, which is the advective term, uh, and this term, which is the Coriolis term. And the ratio of these two terms are basically basically called the Rossby number. And if you see v dot del v, so del is ddx, so there will be v by l and times another v. So this is v square by l, right? And this is v cross omega, right? So this is v square by l, and there is one v omega. So v square by l divided by v omega will give you v by omega l. So this is what the Rossby number um, uh, amplitude is. Right? Now, what does it say is that if you have a very low Rossby number, if it's less than 1, so that means so the Coriolis force is high and the advection term is low. So that in those cases, Coriolis force is important. You cannot neglect that. Whereas if you have Rossby number greater than 1, the Coriolis force is actually low and the advective force is high. So you can neglect the Coriolis force. And as we also earlier saw while doing linear stability analysis, is that this advective term is what is causing these instabilities, because this is a nonlinear term and it introduces this nonlinearities into the system. And this is what is causing the instabilities and the turbulences and all those things when we are doing the instability analysis. And therefore, this Coriolis force is actually helping in suppressing the instability, suppressing the turbulence that is caused due to the advective force. right? So in cases where the Coriolis force is important, that is Rossby number less than 1, we would expect the system to have lower turbulence, lower instabilities. Okay. So yeah, that is all about fluid dynamics in a rotating frame. Okay, so let's take a quick 5 minutes break before we start with. Uh, so we'll do two more topics today. One is so these are all related things. So this is about vorticity in the rotating frame. So earlier we studied Kelvin's circulation theorem and that vorticity is constant. And now we are going to see what will happen if we have a rotating frame. And after that, we'll study this Taylor-Proudman theorem, which is a very interesting thing. And we'll see some videos about how that uh, theorem works in lab experiments and those things. So we'll just come back in a few minutes. Okay. Okay, so let's continue from the uh, Euler's equation in rotating frame. So, in one of the earlier lectures, actually in week 3, if I remember, yeah. So in week 3, we have studied the vorticity theorem and the Kelvin's circulation theorem. Right? So if you remember, this equation is just by taking curl of the uh, Euler's equation. So if you just take curl of this equation, right? So curl of v is omega, and this curl of gradient will vanish, right? So therefore, we are left with only um, curl of v cross omega, and this v dot del v is actually how we decompose v dot del v into into this way, right? So this is a identity where v dot del v is gradient of v square by 2 minus v cross omega, right? So curl of gradient will vanish, and then for therefore curl of v cross omega will survive, and this is what the equation will become. So this is called the vorticity equation, which says that how the vorticity changes in time in the system. So, well, now to visualize vorticity physically, like I mentioned in that week as well, is that this is the kind of, you can think of it as circulation, or well, not exactly circulation, but because we also saw one example where vorticity uh, could be non-zero, but circulation could be zero, right? So it could be like some curl in the velocity field, right? So for example, if you remember, I gave the example of electric and magnetic fields. So electric fields are do not have curls, whereas magnetic fields are have curls. So del cross E is zero, uh, unless there is some magnetic field. But in general, del cross E is zero for a single charge. And on the other hand, del cross B is not actually zero. It is something positive. So magnetic field has a curl. So whereas electric fields are divergent, and they uh, they like you know diverges from a single point of charge. So that is how you can visualize the vorticity. Same thing in place of velocity, right? Curl of velocity. So then we studied this Kelvin circulation theorem, which states that if we have a ring, and within that ring, whatever the vorticity was there at the starting point, it will not change with time. So that is what this expression means. Del t of omega dot ds equals to zero. And we had derived this uh, theorem as well. Okay. Now we want to understand whether this theorem will hold even if we have, uh, even if the frame itself is rotating with angular velocity omega, right? So because there was no rotation of the frame was stationary. So this was what the equation in the rotating frame is, and we do the same thing. We replace v dot del v with this, where omega is del cross v, and this equation reduces down to this equation, and finally we have, uh, well, we take the curl of this equation, and curl of gradient will vanish, so this term will vanish, and this curl of v will give you del omega del t, and curl of v cross omega, and then curl of v cross 2 omega. So you have this extra term that is coming out from this Coriolis force term, right? So we can just simplify this by writing like this. So we can club omega and so small omega and 2 capital omega, and this is how we write the equation. And now similar to this equation, if you compare these two equations, so you can see that small omega is actually replaced by small omega plus 2 omega. Right? So therefore, this condition will be actually replaced by small omega plus 2 omega. So this is actually the how the condition gets modified in presence of, so if you have a rotating frame. So what does this actually physically mean is that, so this, according to the vorticity theorem, it states that if you have no vorticity at the initial time of the system will not have any vorticity at a later time as well. So if omega is zero initially, so del omega del t will be zero forever. But here it states that, you know, so this is basically coming from this equation. Well, I can always write this equation as this because the capital omega is constant. So I can always take it uh, inside the del t. This will be anyway zero. So this is done just to have some symmetry on both sides of the equation. And this just states that how the omega plus 2 omega actually evolve in the system. And it states that even if small omega was zero initially, this right hand side is not going to zero because of the presence of this capital omega. Right? So that means that even if we have no vorticity in the system initially, this rotating frame will introduce some extra vorticity in the system, and that can grow with time, right? And it will not be zero forever, unlike the case for a non-rotating frame. So this is what happens uh, of the Euler equation in rotating frame. Okay, now the consequences of this equation is what we study as this Taylor-Proudman theorem. So we saw that this del omega del t is equal to this, and well, now in a steady state we'll have this is equal to zero, right? So in steady state del t is zero, so this will be zero. Now we impose another condition that the small omega is much less than capital omega. So that just means that the vorticity inside the fluid is not much. So whatever vorticity is should be introduced in the fluid is because of the rotating frame and not because of the inherent vorticity of the fluid. So with that condition, we can neglect omega with respect to 2 omega, 2 capital omega, and this equation will reduce down to this thing. Right? Now from here to here, let me just derive how we go from here to here in just a few steps. So, okay. So what we have is del cross v cross omega equals to 0, right? So if you remember the vector identity, well, you can always check this out. Well, I actually have to check it, what the identity is. Let me just, okay. So the identity for this thing del cross A cross B is actually A del cross B minus B del dot A plus B dot del A minus A dot del B. Right. Okay. So we just use this thing on this thing. So this will turn out to be phi del dot omega plus uh, omega dot del V minus omega del dot V minus V dot del omega. Okay. So this is what it becomes. Now we're going to see that most of the terms will vanish. So for example, this will vanish because the fluid is incompressible. So this is just an assumption that we took. Right? This will vanish because omega is constant. So del dot omega would be 0. And similarly, this will also vanish because omega is constant. Right? So this term will be something like Vx del omega x del x. Right? Well, not exactly. So Vx like this, Vy del omega del y plus Vz del omega del z. But as I said, omega is constant and do not depend on x, y, z, so this term will become 0. So these three terms will vanish, and finally we'll be left with omega dot del times v equals to 0. So this is what we'll be left with. Right? So yeah, that is the final equation that we have. Yeah, so that's how we go from here to here. Now, why do we need to go to here is because, well, this is much simple, but what does this physically mean is that, so omega dot del phi equals to 0. So this is omega x del x of phi plus omega y del y of phi plus omega z del z of phi, right? And well, these are the assumptions that slow, steady because del t is 0, uh, and ideal because we neglected the viscosity, incompressible because we took the assumption del dot v equals to 0, and rotating frame, of course, right? And so basically, so what are the consequence of this equation omega dot del v equals to 0 is that it just says that v does not change in the direction of omega, right? So what does that mean? And we will see that in an experiment, right? So the experiment is that, uh, so for example, let's say you have a jar of water and you are rotating the jar, right? And the jar is rotating about this axis. So this is the rotation axis, and because about which this is rotating. So omega is along this direction, the z direction, if you can say it like that. And it just states that the velocity of the fluid will not be changing with respect to the z direction, right? So it means that if you introduce an obstacle or some perturbation at the base of the jar, so you can you can assume that the fluid will circulate over around this obstacle, right? So the fluid which was rotating uniformly in the rest of the place will have some circulation over here. But instead, what you will actually observe is that the circulation is also present at at various heights of the fluid, even though the obstacle is not present at a very um, high height or far away from the obstacle. The fluid will also have the same velocity as it is having near the obstacle, right? and and it seems like there is some invisible obstacle that is present at all heights along the direction of omega, because v cannot change along the direction of omega. So whatever v is there over here, same v will be there over here, and therefore the fluids will seem to rotate around an invisible obstacle that we see over there. So that we'll see from this uh, simulation. Okay, so okay, so let's just look at this YouTube video and see. Okay, let me just play the YouTube video. Okay. Give me a minute. So that obstacle is basically, okay. Yeah. So that obstacle is basically, causing the uh, fluid to turn around it, right? And therefore, um, huh. But therefore, the fluid will have turn around the obstacle, in this region. But it seems to be a column of fluid, like the whole column of fluid will turn around some invisible obstacle, right? So this is they put some dye on the fluid, and that's how they track the fluid particles, right? So we studied about streamlines, streak lines, and path lines, right? So these are the this should be the streak lines, right? So there they put some dye, and they will start rotating the uh, jar. Yes. So this is the column of fluid is what they are calling the Taylor column, right? So you see that the whole column is basically getting disturbed, right? So about the rotation axis, all the points or all the parts of the fluid will have the same velocity, and that's why they form these column-like structures, because the velocity cannot change uh, along the rotation axis. So now you see that around this obstacle the fluid is uh, passing around the obstacle, but the obstacle is present at the bottom. What is causing the fluid at the top or at some height to go around it, right? So that is what is the cause of this Taylor-Proudman theorem, because along a given column in the direction of the uh, rotation axis, the fluid cannot have different velocities at different parts. Right. So you can check that out. But this is what this Taylor-Proudman theorem talks about, and these are very important in some cases like weather prediction and many other geophysical scenarios. So weather prediction I mentioned because so this winds or uh, this clouds, so they are moving in the atmosphere of the Earth, whereas the Earth is actually rotating on itself, right? So we'll have these columns of winds that are moving around in the atmosphere of the Earth, right? So these are some of the geophysical applications of this Taylor problem theorem, right? So that's it for this week, and for the references, as I mentioned, so this is the book for uh, where you can find the stellar oscillations, and apart from that, I will also share some materials on the stellar oscillation. So I'll upload them in the drive in the notes folder. So maybe you can, like, I don't know if you have already checked it. So there is a link for the drive where I'm uploading all the PPTs and all the notes, handwritten notes, and there I will upload the uh, material for which I showed you, like the paper which showed this thing. And so actually the derivation that we just saw, like up to, you know, well, up to this part of stellar oscillations, like this part, and deriving this equation. So these are already covered in the first maybe few pages of this paper. So yeah, first 8 to 10 pages, and after that it has remaining 18 or so pages, goes on doing further analysis of these modes. So these are, as I said, are very current ongoing research topics, and maybe you can have a look on how people do research on these things. And another material is this thing, which contains the derivation of the equations of these equations, which are not given in this paper. So I have made a separate document on this, which I'll also share. But this is if you want to go through some book. So this is a book for the stellar oscillations, and for rotating fluid frame, as I said, Kundu Cohen book is good enough. And for physics of fluids and plasmas, uh, so this book is the Arnab Rai Chaudhary. So this also contains the Taylor problem theorem and all those things. So chapter 9, I think I also have this book open. Maybe if you just, so this is also a good book from an astrophysics point of view. So yeah, chapter 9 contains hydrodynamics in rotating frame, vorticity Taylor problem theorem, and all those things. Okay. So yes, so this is it for this week. Let me know if you have any questions. So next week, actually,